Alright, this video is going to help us understand one application of matrices, or I should say 1.5 applications, we'll see what that means in just a second, as well as another way to solve matrix systems using determinants. So, two ways in which we can sort of use matrices to have a nice little shortcut are finding the area of a triangle and determining whether or not points are collinear, whether or not they lie on the same line. So the nice part about determinants, as far as angle of triangle or area of triangles goes, if we were looking at the triangle over here on the graph, if we were looking at these 3 points given, -3, 5, 2, 6, and 3, -5, in order to find its area, we would have to decide of which side we wanted to have be the base. We'd have to drop an altitude in there normally, right? We would take our geometry class and we'd apply it here, drop an altitude down and draw that right angle. We have to find that height, and then we could multiply 1/2 times the base times the height, right? So I got to find the distance formula, and I got to do some distances here and find the point where they cross. There's a lot of geometry going on. Well, there is a nice shortcut. To find the area of a triangle using matrices, we don't need to do all of that. You'll notice the half in front, very similar to that 1/2 base times height, but in order to substitute out that base and height, what we can do is find the determinant of a 3×3 matrix where our 3 points become columns 1 and 2. So notice we got x, y, x, y, x, y. So we got the line there. And then we fill in that third column of 1s. Now some people might say, well, why don't we just fill in them with 0s? If it's not really there, let's make it 0s. Well, remember, when we find determinants, we tend to do a lot of multiplying the diagonals. And if we fill in a whole row of 0s, think back to our minors and cofactors way of doing things, that would just make the entire determinant 0 every single time. Whereas if we're multiplying, again, those determinants, multiplying by 1 really doesn't change anything, which should make it fairly simple. In fact, if you want to choose that row almost every time, if you don't have any 0s going for you, that actually be a pretty easy row to take advantage of to find the determinant. So let's do that here. I'm going to pause the video now. I'm going to set up a 3×3 matrix and work out its determinant to help us find the area of this triangle, and then we'll do the same thing for the area of the bottom triangle. Alright, so here's our information for us. Again, what I did here was, up on the top one, again, we've got our points laid out in columns 1 and 2. We took the determinant of those points and got a -56. Now, you notice I didn't lay out all the minors and cofactors to do that 3×3 determinant. Instead, what I did was went ahead and threw those onto my calculator. So if we enter that matrix, that 3×3 matrix in our calculator, -3, 5, 1, 2, 6, 1, 3, -5, 1, all I have to do is go to second matrix here, and if I go over to my math menu, you'll notice the very first option on our menu is determinant. We do that quite a bit with matrices, so they make it option number 1. So I'm just going to say find the determinant of matrix A, throw our parenthesis there, and hit enter, and we get that nice -56. It makes a really easy way to find determinants, which is what makes this method so fast. Which means, again, our determinant's -56. Now, we bring up kind of an awkward part to this. You might have noticed in the formula it said plus or minus. Now, the area of a triangle shouldn't have two different answers. But what you have to remember is the area of a triangle should also never come up negative. So if we happen to get a determinant like -56 that comes up as a negative number, we technically just want the -1/2 to be multiplied by that. We have to make sure our area comes out positive. Now you might say, well, why not just say absolute value then? Well, with those straight bars being determinants, that looks really confusing. To say absolute value of the determinant of, those symbols get very kind of mushed together. So since we're going with determinant symbols, we'll just say plus or minus. Just know that we're picking the one, right? Whether it's positive or negative. Picking whichever one of those two gives us a positive area. So our final area over here would be 28. And again, this would be units squared, or whatever, miles squared, inches squared, square inches, I should say, on our graph. Area of the triangle at the bottom, same thing happens. Again, we found the determinant of the 3×3. This time it came out to 0. Now you might say, how can a triangle have an area of 0? Well, if we take a good look at it, if we plot those 3 points, 0, 1, right, it's going to be somewhat in this area, 2, 2, again, it'd be kind of over here, and if we look at it, 8, 5, so kind of go way out here and up here, you might notice something about those 3 points. Right? They don't form much of a triangle. The only way that 3 points could ever come out to a 0 area is if that triangle has 0 area, or basically those 3 points are what we call collinear. Fix the font there real quick. There we go. Collinear. Because 3 points that are collinear won't form a triangle. They form a straight line. And of course the area of a line is 0. So that's one really fun way to kind of know whether or not 3 points lie on a straight line. Again, the other way we'd have to do that would take a lot of work, finding the equation of the line and then verifying that the third point, or all 3 points for that matter, lie on that line. Much faster just to find a determinant. If the determinant is 0, find the determinant of that 3 by 3 matrix. If that determinant is 0, then we know they're collinear. So here's a fun problem on the next page for you. Go ahead and try out those methods. I'm going to go ahead and throw the answer on here for you and see if you can find the area of lake history, as well as determine down here, right, if I could buy lakefront property if I lived in Picardville, or Picard Town, sorry. All right, so I've got all the work worked out for you here. What I did is I went ahead and called Millerville 0, 0 on my graph so that I could measure everything from that point. So then I put my points in 0, 0, again 4 miles east and 2 miles north, 8 miles east and 10 miles north. Found the determinant. Again, row 1 was very helpful with 0, 0, 1, which meant basically 40 minus 16 was 24. Because that's already positive, I don't need the plus or minus. So therefore half of 24 is 12, and we've got 12 square miles. For the question at the bottom, is Picard Town basically collinear? Is it lakefront property? Well, realize that it is 6 miles east and 4 miles south. So the question is it on that lakefront property or not? Well, is it collinear with BC and BR? As we notice from its determinant, no, it's not. It didn't come out to 0, which means if they're not collinear, it's not lakefront, and therefore we've answered our question. Now, finding areas of triangles is one really good use for determinants. Makes it really fast when you sort of have 3 random points on a graph. Another nice application is what's called Cramer's rule for solving systems. Cramer's rule is basically a way to use determinants to solve a system very, very quickly. Not quite as quick maybe as RREF or inverse matrices, but again, it's a helpful thing. So we'll go over it fairly quickly. The idea of Cramer's rule is this. We're going to take the coefficient matrix from a system of equations. So you'll notice A, B, C, and D. We're going to divide by the determinant of that coefficient matrix. So to find X or to find Y, I'm putting that A, B, C, D determinant matrix on the bottom. Then to find X, what I'm going to do is take out the X coefficients, and I'm going to insert my constants. So notice E and F from the right are going in place of that first column. Whereas if I'm trying to find Y was the second column in my determinant, or my coefficient matrix here. So I'm going to take out B and D, and I'm going to put in E and F when I'm solving for Y down here. Right? One thing you'll notice is, again, you won't be able to solve that system if that determinant comes out to 0. Same reason we did when we had inverses. Right? When we solved by inverses, if the determinant was 0, that means there was no inverse. Basically, we wouldn't be able to solve that system. So take a second, think about this system here at the right. See if you can't set up those determinant matrices. Find the determinants and quickly solve the system. All right, so over here at the right, we've got these determinants all set up. You'll notice again the coefficient matrix on the bottom, 4, -2, 3, -5, becomes the determinant in the denominator down here. The determinant came out to -14. And then on the top, if I want to find X, replace column 1 where the X's used to be with 10 and 11. When I'm finding Y, I'm going to replace the -2 and the -5 where again the Y's used to be. I'm going to replace them with 10 and 11. So again, the top one came out to -28 divided by -14 means that X equals 2. And again, the 4 times positive 11 minus 30, well, 44 minus 30 is 14, divided by -14 would be -1. And we've quickly solved our system to be 2, -1 for an answer. Now you might be saying, well, with 2 variables and 2 equations, we could do a lot of different things. There's RREF, there's inverse matrices, we could just solve by hand, elimination, substitution. But what about when we have a slightly larger system? Right? Again, 3x3s are 3 variables, 3 equations, always made for a little bit more work. Well, with Cramer's rule, the setup takes a little bit of time, but after that, it's pretty fast, pretty quick, and pretty easy. We would just need our coefficient matrix. So again, -1, 2, -3, 2, 0, notice no y in that second equation, 1, and 3, -4, 4 over here at the right. Find its determinant, which we can quickly do using our calculator, right? And we've got our determinant of 10. That means I'm going to set up each one of my equations, right, for my variables with a 10 in the denominator. Then for x, again, I'm going to put 1, 0, 2, right? These constants over here, 1, 0, 2, I'm going to put into column 1 for x, column 2 for y, column 3 for z. Notice all the other numbers stay where they were from that coefficient matrix. Find a few determinants. So this one came out to 8 over 10, -15 over 10, -16 over 10, and reduce a little bit, and we have our answer. It's pretty fast, pretty quick, and pretty easy way of solving a system using simply determinants. If you have any questions, make sure you ask your teacher. Otherwise, good luck and happy matrices.